Hello everyone, welcome back. In this video we're going to be talking about the t-test. So first let's go back to our figure. And remember, our figure will help us identify if we're choosing the correct statistical test. So we'll start with our data type. The student's t-test is under the continuous data type, and this is used when you're looking at two groups of patients. The t-test is going to be comparing the means between the two groups, and there's two types of t-test we'll be talking about today, both the paired and unpaired, depending on how the study was conducted. So let's get started. The t-test for unpaired data is called the independent samples t-test, or students t-test. And our first objective is going to be to analyze if a student's t-test was appropriate for analyzing a specific endpoint within a journal article. And so the first question is, well, what is the student's t-test used for? And as I said before, it compares the means between two mutually exclusive groups. And again, because it's an unpaired test, we're looking at between rather than within. There are some assumptions that you have to meet to use a student's t-test. This is actually going to be one of the most common statistical tests that you're going to be seeing used within trials. So let's look at some of those assumptions. The first assumption is that the dependent variable, or the outcome, is on a continuous scale. The second assumption is the sampling distribution is normal. Remember from one of our previous videos that standard deviation not greater than mean. And also to meet the central limit theorem, which means sample size needs to be greater than 30 or 20 degrees of freedom. And we'll abbreviate degrees of freedom df. The third assumption is that the independent variable is mutually exclusive and dichotomous. And what this means in non-statistical terms is that there's two groups and you can only be in one group or the other. Our fourth assumption is that variance is similar between groups. We can determine this by looking for the standard deviation, because variance isn't usually listed within the study results. So we'll need to find the standard deviation, and the variance is just the standard deviation squared. So for example, we could, if we found a standard deviation between two groups of, one group had a standard deviation of 3 and the other one had a standard deviation of 10, we would square each one of these numbers. So that would give us, if we squared both of those numbers, it would be 9 and 100. Now we would want to take the ratio of the variance, and if it's more than 10 to 1, so if ratio greater than 10 to 1, the variances are going to be different. Therefore, we'll have to use a ordinal test for this type of data. Now, this is a rough way of looking at variance, but I think this is the simplest way for you guys at this point. And the last assumption is that observations are independent. And remember, this is because we're looking at the unpaired test. Each participant only provides one data point. So let's do an example, and we'll do some calculations of using the t-test, and this will help us really see the process of statistical tests a little bit easier. So our first example, we have we're testing a miracle weight loss drug versus placebo. And so patients are going to be randomized to one or the other. We have 41 patients in both groups. The results show with the miracle drug, patients lost a mean of 10 kilograms, and that's plus or minus 2 kilograms for the standard deviation. And then we can look in the placebo group, and the placebo group lost 1.5 kilograms, and that's plus or minus 3 for the standard deviation. One of our colleagues that is great with the statistical tests says you should use a student's t-test. Well, let's figure out if he's right. So the first thing that we need to do is make sure that none of the assumptions that we talked about were violated. So let's scroll up. The dependent variable is continuous because we're looking at the mean value for weight loss, and that is a continuous variable. The standard deviation is not greater than the mean, and the sample size is greater than 30, so we meet both of those criteria. The independent variable is mutually exclusive, so they're either getting a placebo or the active drug, and you can only be in one of the groups. And the variance is not greater than a 10-to-1 ratio. If you squared both 2 and 3, it goes out to 4 and 9, and there's not a difference of 10 within the ratio. And then the last assumption, being that observations are independent, is also true. So step 1, doing the test, is make sure no assumptions are violated. Step 2 is to state the null hypothesis and the alternative hypothesis. So our null is going to be, and we'll do these as two-tailed tests. We'll talk more about two-tailed versus one-tailed tests in the next video. But our null hypothesis is that miracle drug has no effect on weight loss. And the alternative hypothesis is that the miracle drug has an effect on weight loss. So to do that, we need to state our alpha next. So let's set our alpha at 0.05. Remember, that's a 5% chance of a type 1 error occurring. Our p-value needs to be less than alpha for the results to be statistically significant. Next, we should calculate the degrees of freedom. Degrees of freedom are calculated differently for each statistical test. I'll show you how they're calculated for the t-test. So degrees of freedom are calculated as the number of patients in the first group, so we'll just call that N1 minus 1, plus the number of patients in the second group, N2 minus 1. And that is how you calculate degrees of freedom. And since we know that there were 41 patients in each group, that goes to 40 plus 40 is 80. So 40 plus 40 equals 80. Now we'll use the degrees of freedom to find the critical t-value. So let's talk about the critical value, and in this case it's going to be the t-statistic. When we calculate the t-test, we end up getting a t-statistic. The test has to be either greater than or less than a certain number. When it's greater than or less than a certain number, our results will become statistically significant. So how do we find this? There are tables that are available that contain all the t-values based on the degrees of freedom, the number of tails that you're using for your test, and the alpha. So let's pull up a t-table. So here is our t-table. We talked about using a two-tailed hypothesis, and we want our alpha for our two-tailed to be 0.05. So we're going to be in this column here. Now on the left side of this table, we see our DF for degrees of freedom. Remember, we calculated that we had 80 degrees of freedom, so we need to scroll down here until we see 80, and now we see 80 on the left, so we go from here to here, and we make sure we're still in the right column, and we get our critical t-value of being 1.99. So let's write that down. So our critical t-value is 1.99, which means that when we calculate our t-statistic test, we need to either get a value of greater than 1.99 or less than negative 1.99 to get a statistically significant result based off our alpha, number of tails, and our degrees of freedom.
So now let's go ahead and calculate our t-statistic. To do this, we first need to calculate the sum of squares. While this may sound daunting, it's very easy, and all you have to do is multiply the variance times the degrees of freedom for each group. So in our example, we had an active group which had a standard deviation of 2. The variance is the standard deviation squared, so 2 squared is 4, and then we figured out before that there was 40 degrees of freedom, so we multiply 4 times 40, which just gives us 160. And then for the placebo group, we had a standard deviation of 3, and if we square that, we get our variance of 9, and we multiply that by the number of degrees of freedom, and so we get 360. Now we use the sum of squares to calculate the pooled variance. So the pooled variance is equal to the sum of squares for group 1, and I'm going to just abbreviate that SS1, plus the sum of squares for group 2, divided by the degrees of freedom for group 1, plus the degrees of freedom for group 2. And so that would be 160 plus 360 divided by the 40 plus 40 degrees of freedom, which if we put into a calculator gets us a number of 6.5. Now we use the pooled variance in the t-test calculation, and I'm going to go over the calculation now. So the first part is you subtract the mean of one drug or one group from the other group. In this case it's a placebo. So that's the first step of calculating the t-statistic. And then we divide all of that by the square root of the pooled variance, which was the 6.5 number we calculated in group 1, divided by the number of patients in group 1. And then we add the pooled variance in group 2 divided by the number of patients in group 2. So that's how we do the calculation. So in our example, we had a mean weight loss of 10 kilograms in the active group, and so we subtract the mean weight loss in the placebo group. So 10 minus 1.5 kilograms, and we divide that by the square root of the pooled variance in group 1, which is the pooled variance is going to be the same in both groups, divided by the number of patients in group 1. Then we add the pooled variance divided by the number of patients in group 2, which was the same. So that gives us a mean difference of 8.5 kilograms divided by the square root of 13 over 41. And if we put that into our calculator, that would give us a t statistic of 15.09. Now, because this is greater than our critical value, then our test will be statistically significant.
And what we can do further is plug this information into an online calculator to get our p-value. So let's go ahead and do that. Here's the link for the statistics calculator we'll be using, so you can follow this. Now when we get here, we'll see that there are a number of things here. So we'll want to scroll down to t-distribution, and we'll want to get our p-value calculator for a student's t-test. And here all you need to do is enter the degrees of freedom, which we already determined to be 80, and our t-value, which was 15.09, and you just hit calculate, and we actually get our p-value is going to be so small that it can't detect it. So and that's because we see such a big difference with weight reduction in this study, and also our standard deviations were rather small too. All those things lead to a lower p-value. Let's lower that let's pretend that it wasn't as big of a difference. Let's say our t-value was only 4 instead of 15, and now we still see that with a two-tailed probability our result is still very significant. Now let's even lower that even more. Remember, our cutoff point was 1.99. So if we use a t-value of 2, we see with a two-tailed probability, our test is right below that significant cutoff point of 0.05. Now if we change it to 1, remember our critical value was 1.99. Let's see what happens. And it shows that in this case, if our t-value was 1, our probability would be non-significant. Our p-value would be 0.32. It would be greater than the alpha.